In this video, we are going to discuss about nth root of a complex number. At the end of watching this video and doing the assigned activities, as a learner, you will be able to understand the concept of nth root of a complex number, apply knowledge to calculate nth root of a given complex number, demonstrate the ability to express nth root in both polar and rectangular forms, and draw a diagram of nth roots of a given complex number. As a prior knowledge, you need to understand the de Moivre's theorem, which tells that if z is a complex number in the polar form, then the nth power of z is equals to r to the power n times cos n theta plus I sin n theta. For the instructional process, we use interactive simulation to visually represent the nth root of a complex number. Please try it for better understanding. On your screen, you can see the link of this simulation. Please click in this link and try to understand the concept. What does the nth root of a complex number represents for? Please note that the nth root of a complex number are evenly distributed in a circle by angles 2 pi by n. Any non-zero complex number can have exactly n distinct roots. The roots lies in a circle of radius, the absolute value of z to the power 1 by n, which centered at the origin and is spaced out evenly by angles 2 pi by n. Each of these roots are, let's say rk equals to n root of r times cos theta plus 2 pi k by n plus I sin theta plus 2 pi k by n, where k runs from 0 to n minus 1. Each value of this k gives the root of the complex number. By using de Moivre's theorem, we will be able to derive this formula of nth root of complex number. Let nth root of the complex number z is w, which is capital R times cos phi plus I sin phi, such that the nth root of z equals to w. That is why w to the power n equals to z. Now we will substitute the value of w and z. Applying de Moivre's theorem, we will get this expression. As we know that let z be a complex number, then by de Moivre's theorem, the z to the power n equals to r to the power n cos n theta plus I sin n theta, which we have applied here. Now, equating the real and imaginary parts separately, we get r to the power n equals to r, cos n phi equals to cos theta, and sin n phi equals to sin theta. By ordinary simplification, we get r equals to nth root of small r and n phi equals to theta plus 2 pi k, because sin and cos both are periodic function whose periods is 2 pi, and to get the valid values for both cos and sine, it comes in the period of 2 pi. That is why the n phi equals to theta plus 2 pi k. With a bit of more calculation, we will get phi equals to theta plus 2 pi k by n. Thus, the nth root of complex number z is w equals to r cos phi plus I sin phi, which is w equals to nth root of r times cos theta plus 2k pi by n plus I sin theta plus 2k pi by n, for k runs from 0 to n minus 1. Here we have simply substituted the value of capital R and phi from above calculations. So this is what we call the nth root of a complex number z. Now we will see one example. In this example, we will find the square root of I, where I is a complex number. So to solve this problem, we will use the formula for the nth root of a complex number z. Since I is a complex number, the magnitude is 1 and the amplitude means the argument is pi by 2. Therefore, the extended form of complex number I is cos pi by 2 plus I sin pi by 2. With this, we will be able to find the square root of I, means two different roots of a complex number I. That is why the roots will take when the value of k is 0 and k is 1, because the value of n is 2 in this case. Taking the value of k equal to 0 in the formula, we will get that cos theta plus 2 pi k by 2 plus I sin theta plus 2 pi k by 2. Here the value 2 is replaced in the place of n in the formula. Now we will put the value of k equals to 0 and we get the answer cos theta by 2 plus I sin theta by 2. Then The solution is cos pi by 4 plus I sin pi by 4, and which is in the rectangular form 1 by root over 2 plus I 1 by root over 2, where the first root is labeled by R1. Now we will find the second root R2. For this we will take the value k equals to 1. Putting the value k equals to 1, we will get that the answer is cos theta plus 2 pi by 2 plus I sin theta plus 2 pi by 2. With this, the solution is cos 5 pi by 4 plus I sin 5 pi by 4. And in the rectangular form, the answer is 1 by root over 2 minus I 1 by root over 2. On the screen, you can see the square root of I, which are labeled. Now, for your better understanding, here is a problem which is based on real life situation, and it is suggested to you to solve it. Impedance, which is a concept used in the field of electrical engineering and physics to describe the flow of alternating current AC. Impedance is the combination of resistance and reactance, and it is represented by a symbol Z. It is expressed in terms of ohms. In a circuit with both resistive and reactive elements, impedance is a complex quantity typically denoted by Z equal to R plus Ix, where I is the imaginary unit. Here is a question. In electrical engineering, a circuit has an impedance represented by the complex number Z equal to 8 plus 6I. The engineer need to design a component with an impedance that, when cubed, matches the original impedance. Now solve the following questions. Calculate the magnitude of Z and amplitude theta. Determine the cube root of the original impedance in a polar form. Design a new component with the impedance Zn such that cube of Zn matches the original impedance. And express the new impedance in a rectangular form and calculate its magnitude and angle. With this, thank you very much for this video. Please feel free to write if you need any further information.